Okay, welcome to Pre-Calculus Unit 3, Lesson 4, just after the first quiz. First of all, if you haven't done so already, I encourage you to just pause right away and read through the first couple of pages of the notes just so that you can kind of review. Also, on this first page here, you'll see that there's a couple of key things about transformations from Algebra 2, just in case you've forgotten them. The real key idea is that the order of transformations really matters. We want to go ahead and do any reflections first, then we want to go ahead and deal with any stretches or dilations, and then finally we'll take a look at any translations, as they're often the easiest. We'll save those till last. Taking a look at the first example, what we've got to do here is we've got to look at how the parent function g of x equals sine of x has been transformed to produce this function f of x. So if we start off with the function sine of x and we analyze and look at the function f of x to see if there's any reflections, it's clear that we've got this minus sign here. If we've got the function sine of x, which typically looks like this, if we now multiply it by a -1, we're going to get negative sine of x, and that right there causes us to reflect across the x-axis. So our first transformation is an x-axis reflection. Up next, we look to see if we've got any vertical or horizontal dilations, and if you take a look up the front, you can see that there's also a 2 there. What that does is it causes all the y coordinates to double. It's a vertical stretch. So instead of oscillating between 1 and -1, our function is now going to oscillate between -2 and 2. That's a vertical stretch or vertical dilation of scale factor 2. And then finally, we can see that instead of x here, where we previously saw x, we're going to replace it with x minus pi. And what that does, that's going to move our function to the right pi units. So instead of finishing its period at 2 pi now, it's going to start its period at pi and finish its period at 3 pi. There's no change in the period, it's still 2 pi. Just where we start and where we finish has changed. Of course, I've only drawn one cycle here. You'll be expected to draw a full graph for your function. So our final transformation, as we mentioned, there was a horizontal translation to the right of pi units. Taking a look at this next example now, we're looking at how the tan function is going to be transformed. And remember that the tan function itself, you'll remember from Algebra 2 last year, looks like this. It has asymptotes at -pi/2 and pi/2, and its range is really from -infinity to infinity. It kind of looks a little bit like a cubic graph. So the first thing we need to do is, are there any reflections? Can't see any minuses, so we're looking good on reflections either across the x or y axis. The next thing we're looking for is stretches, and you'll notice that we have this 3 here. Now, anytime you replace x with 3x, what that's going to do is it's going to have an impact on the period. In fact, it's going to be a horizontal dilation of 1/3. What's going to happen is the period is going to reduce by a factor of 1/3. And so our new graph is actually going to be having asymptotes. All the x values are going to divide by 3 essentially. So -pi/6 and pi/6 will be our new asymptotes. Notice, by the way, that the period for the parent function was pi. Now the period for our transform function is going to be pi/3. So that's our first transformation there. And then finally, if we go ahead and we replace x with x minus pi/6, very similar to the previous example, we know that that's going to shift us to the right pi/6. But if we go ahead and we simply add a 1 at the end there, which brings us to our function f of x, what that's also going to do is give us a vertical translation up 1. So over here was our previous tan function. We can kind of break that translation down into 2 parts. A horizontal translation of positive pi/6, and then also a vertical shift up, positive 1. And so if you're going to go ahead and graph that, what it would look like, well, we've just said that we're going to shift to the right, so our asymptotes are now going to be at 0, and they're going to be at 2 pi by 6, which is 3 pi by 3. And we're also, our midline is now going to have shifted up and be at y equals 1. And so we're going to end up with a function that looks something like that. Again, most of this is review from Algebra 2, and hopefully you'll remember that one of the most important things is to make sure that we actually get our function in the correct form so that we can easily see all of the transformations. So I'm just going to rewrite this here as 1/2 times x minus pi, simply because that helps me to go ahead and see the key transformations there. Of course, that's not plus 1 at the end there, it's minus 1. And so go ahead and take a moment now and see if you can have a go at this one yourself. I'm going to pause and work it out myself, and then we'll share our answers in just a moment. All right, so here's the function that you should have put together. Some of the key characteristics. First of all, we can see, because the leading coefficient is 2, that the amplitude has to be 2. We've got that value of 1/2 just there outside the parentheses, so we can see that the period now has to be 2 pi divided by 1/2, which is 4 pi. And then you can see that the phase shift, which is really the horizontal translation, we're going to move to the right pi. And finally, the midline has to be the line y equals -1. What I like to do is I like to go ahead and think about the horizontal translation first of all. Then I'll get in play the midline, and I'll think about the range of the function. So what's the maximum value and the minimum value? And then I'll break down the function into quarter of the period. So if I know the period is 4 pi, then 1 pi is a quarter of the period, and that's where these lines have come from here. Then I know that a cosine function starts at a maximum. For the first quarter of a period, it goes to the midline. Then it goes in the next quarter to the minimum, and then the next quarter it's going to go back up to the midline. In the final quarter, it will go back up to the maximum, but I don't have enough space for that. And so what I've done is I've continued the graph in the opposite direction, just to make sure I'm filling the full space of the axis there. Okay, in this next example, we're faced with deriving the equation from the given graph here, and we've got to use cosine. So what I'd encourage you to do, first of all, when you're using cosine, we know it's either got to start at a maximum or start at a minimum, depending on whether or not we've reflected it vertically. What we'd like you to do is we'd like you to try and identify the smallest possible phase shift, the smallest possible horizontal translation. And so for me, that smallest possible horizontal translation moves me to the left here, and I'm going to just isolate this piece here as my first period. I'd encourage you to do the same, and what I'd like you to do is just pause, have a quick go at this problem yourself, and then again we'll check our answers together in a moment. Okay, welcome back. So hopefully when you analyze the graph, you established first of all that the amplitude was 3. The way that we determine the amplitude is we take a look at the maximum y value and the minimum y value, and then we divide that through by 2, the difference between the two. For the midline, it's just bang in the middle between the maximum and the minimum, so we average the maximum y value and the minimum, and you should have a midline of y equals 1. That also helps you to confirm that your amplitude is in fact 3 units. For the period, we can see that if the distance from maximum to maximum is pi units. So if we know that the period itself is pi, then 2 pi divided by b has to equal pi, and our conclusion therefore is that b is equal to 2. And then finally, we can see quite clearly that this function has been shifted to the left, pi by 6 units. So that's our phase shift right there, pi by 6. And so we should end up with a function that looks like this. F of x is equal to 3 cosine of 1/2 into x plus pi by 6. And then we need to go ahead and also add that 1 at the end there. All right, for the final problem of the day, we're going to do a little bit of review on composition of functions. What we've been given is 2 functions here, h of x and f of x, and we've been asked to find the period and amplitude of the composition h of f of x. So I'm going to ask you to pause here and have a quick go at this problem yourself, and then we'll cross-reference answers. So the most important thing here is remembering exactly what a composition of functions looks like algebraically. And so we've started the process here. Really, h of f of x is asking us to take the function f of x and place it into the function h of x. And so when we do that, we end up with the following expression, sine and then 2, where we previously saw x, we're going to replace it with f of x, and the function f of x is 1/4 x minus pi. Let's not forget that we've also got this minus pi by 2, and we've got this plus 1 at the end. Take a moment to tidy that up for yourself now. So when you tidy up that function, you should end up with something that looks like this. And the key things to pay attention to here are really the leading coefficient, which is 1. That tells us that the amplitude has to be 1. And then the other key item here is this coefficient here in front of x. We know that normally 2 pi divided by that coefficient equals our period. And when you work that through, you're going to end up with 4 pi is your period for this composite function. All right. Again, if you have any questions, please make sure that you drop by to any of the extra help sessions. The assignment for today is listed here at the bottom of your notes. Best of luck making a start on that. And again, remember to drop by should you need any help.